A digital signal can only take on a finite number of values. We talked about temperature. Temperature can take on any value in the physical world. However, a signal that allows the display of the temperature measurement on a digital readout will not be able to display all the every. It'll only be able to have an integer display. So suppose that the digital readout is 3 digits and it can display numbers from 0 to 100. That's our digital readout. And assume the temperature sensor is calibrated to measure temperatures from 0 to 100 degrees centigrade. And the output sensor ranges from 0 volts to 5 volts. So we have to correlate the temperature to the voltage. So each digit on the display, 1/100th of 5 volts range, or 0.05 volts, which is 50 millivolts. So each digit on the display represents 50 millivolts. So 50 millivolts, we'd end up with 1 degree centigrade. 100 millivolts, 2 degrees centigrade. 110 millivolts, still 2 degrees centigrade. So the digital readout that quantizes, or there's a quantization of the sensor output to the voltage, and that's how we digitize it. If we could represent it continuously, we could represent it as a linear function. We'd have our voltage versus temperature. As the voltage increased, it's really actually as the temperature increases, the voltage response increases. So we have our voltage is equal to some slope times the temperature. That slope we can get from this linear graph as being 5 volts divided by 100 degrees centigrade. That's the maximum there. And it does have a zero crossing, 0, 0. So our plus B is 0. So we can say that our output voltage then is just 50 millivolts, or 0.05, times the temperature, and we get our linear function. However, the digital representation of that, it looks a little bit different. It looks more like a step function. So again, if we were at, if the temperature sensor was at 10 degrees centigrade, we'd be up here at 500. Our voltage response would be 500 millivolts, and we would display 10 degrees centigrade on our display. However, if it was at 10.5, if I'm reading this up right, if it's at 10.5 degrees centigrade, we'd still be showing 10, right? However, 10.6, we'd still be showing 10, so there's no rounding going on. Once it got to 11, then we'd jump up and we'd start displaying 11 until we got to 12, and we'd jump up to 12. So that's what the digital representation of our analog signal is going to look like. This is just going from 0 to 20 degrees centigrade, this portion of the graph. So for example, if we think about this example, the digital readout of the thermometer in a Lexus model car in the United States usually increases and decreases by 2 degrees Fahrenheit, although sometimes it'll increase or decrease by 1 degree Fahrenheit. So pause the video and think about this digitization, this quantization, and the conversion from Fahrenheit to Celsius, and see if you can determine why you think that might happen. If our conversion for temperature degrees Fahrenheit, that's 1.8, or approximately 2, right? It's 1.8 times the temperature in centigrade. So a degree centigrade is 5/9 of, or 1 over 1.8 of a degree Fahrenheit. If our degree Fahrenheit is 1.8 times a degree centigrade, we add the 32, but each degree centigrade is almost 2 degrees Fahrenheit, right? Not quite. So a Lexus is built in Europe, or in Japan actually, where they use the temperature system of centigrade. And these model cars then probably use the same temperature gauge there, and then just do a conversion from Celsius to Fahrenheit. So that's what happens when something is digitized, right? So if they're built for a degree Fahrenheit system, we'd go back and we'd change our conversion back here so we get each degree Fahrenheit would be able to be displayed on the screen. All right, so that's an example. If we, again, digital versus analog systems, an analog system that's less tolerant to noise, whereas a digital system is more noise tolerant, except if you get, a lot of bit errors. If a one becomes a zero, then that excessive noise, then it could be an error that can't be corrected, and then it could be a very big problem. Um, and this is an example of missiles being fired off. So that's what's going on when our Army completely hits the wrong targets, or I guess our Air Force. But what we can do is we have error detection and correction systems, and we'll look at some in this class. But to add the error detection and correction systems, that requires more bits, so it requires more bandwidth for that. So an analog system, it's in real time. It makes good use of the bandwidth, so that the bandwidth and the data transmission rate. So it's easier to manipulate mathematically an analog signal than a digital signal, but it requires amplifiers, which add noise and distortion. It also requires receivers and transmitters that are designed specifically for that particular system. If you have a new system, you'll change the analog signal, you need to completely change your transmitters and receivers. Whereas in a digital system, you can standardize your receivers and transmitters. And the digital amps also don't distort the signal, but you don't get as clean a signal. If you're into sound, the old analog amps using vacuum tubes sound much better than the newer digital amps that use transistors. All right, and but the key thing here is the signal can be dealt with in software, so that's cheap and easy to change, and we'll look at that also in this class. So which is better? It really depends on the type of signal, the type of system you're working with. Modern digital systems require more expensive components. If we compare this, is comparing TV sets, old TV sets to new TV sets. But if you just look at the price of your iPhone or your Droid phone, they're between $500 and $1,000. That's much more expensive than older phones that just did one thing, right? Analog systems also need to be built with a complex array of op amps, resistors, capacitors, and diodes, while a digital system can be implemented with generic microcontroller and some quick programming. So it makes for the field of programming much bigger. So there's some differences. Key digital advantage: most digital devices are programmable. Same hardware can serve in different applications. You can improve the reliability of the signal with error detection and correction codes, and so that reduced cost due to advances in integrated circuit technology. Digital building blocks make design easier than designing at the transition level, and we'll look at that further in this module as well. But a system itself will include both analog and digital signals on the same board, so we have to be aware of that when we're working with our design, and we'll look at that, of course, later in the course.